So today at JIPS, we're very happy to have Frank Aurzada from TU Darmstadt, who will be telling us about persistence probabilities via perturbation theory, autoregressive and moving average processes. Please.
Okay, thank you, Naomi. Thanks for the invitation to this seminar. So first, let me say that this is joint work with, on the one hand, Sumit Mukherjee and Ofer Zaitouni, and on the other hand, with Marvin Kettner and Christoph Profeta. So there are 2.5 papers that I'm going to talk about. I will touch only the first one, and my main focus will be on this perturbation theory approach, which is part of the second and the half project. Okay, so my agenda is as follows. First, I would like to tell you what are persistence probabilities, because even though there are experts here, I'm not assuming that everybody is familiar with this topic. And in the second part, I will talk about persistence probabilities for Markov chains and how they relate to eigenvalues of certain operators. So I will want to say how this probabilistic problem of computing persistence probabilities is related to computing eigenvalues of certain operators, which are related to, in this case, the Markov chain. And then in part 3 and 4, I would like to apply this to autoregressive processes. So this is sort of the first example, and I will tell you what we know about persistence probabilities of autoregressive processes. And then I would like to introduce this perturbation idea for autoregressive processes of order 1, and introduce this. And the fifth part is another example, which is moving average processes. And there I will try to speak about the same program, and then I will summarize it. Okay, so let's start with what are persistence probabilities. Here's the sort of statement of the problem. The problem is very easy to formulate. Assume you are given a real valued process, x0, x1, x2, and so on. The only thing we are interested in this talk is the probability that this process does not become negative. Yeah? So in a picture, you have here this process. You have a boundary here, which can be 0, which can be some other boundary. And we are asking, what's the probability that this process does not become negative, say, until time n, and n tends to infinity, so for a long time. And clearly, my picture is somehow misleading. It somehow suggests that the process might remain close to the boundary. Obviously, what you will see is that you get a push from the boundary. So somehow the whole area of persistence probabilities and whatever is related to this concerns the question of understanding the push that the process gets from this restriction, from this constraint. So it's a sort of problem of having stochastic processes under constraints and understanding them. Okay. In this talk, we'll see stationary processes. So what we expect is an exponential decay of this probability. Yeah? So if you think of this process being stationary, so the process sort of tries to pass the boundary and this is sort of giving this exponential decay. So the question we are asking here is, given a process, so given xn, what is the exponential decay rate? And in this talk, I will call this exponential decay rate the persistence exponent. Some people call theta, so if lambda is e to the minus theta, theta the persistence exponent. But in this talk, I will not work with theta, I will work with lambda. So I will call lambda the persistence exponent. It may happen that lambda is 0 in the sense that this probability decay is super exponential. Yeah, so then the notation is maybe not completely correct, but I think you know what I mean by this. So lambda equal to 0 means super exponential decay, and lambda equal to 1 means something that is going to 0 slowlier than exponential. Okay, so that's the main question for this talk. Given a stochastic process, what is the exponential decay rate of the probability that it does not leave the non-negative half-axis? What is also of interest, I mentioned this already in on the last page, is what people actually want to understand is is sort of the conditional law. So the law of the process conditioned on not passing the boundary. And that's sort of understanding this push. I'll not talk about this at all in this talk, and I just mentioned that very little is known. Let's say little is known about this. Okay, so why do people study this question? Why do I study this question? As for me, I think this first bullet point is sufficient. So it's sort of a classical problem, and as I think interesting and often quite difficult, even though it's very easy to formulate. I also mentioned that this is sort of falling in the area of studying stochastic processes under constraints. And the term persistence probabilities comes from physics. So there, in physics, it sort of, this persistence exponent is taken to be a measure for a time that a complicated physical system needs to return to equilibrium. So I will just very quickly try to convey this intuition. I'll not use this particular example later on, but just to give you an idea what is sort of the source of this in physics. So consider some complicated physical system. So here you have a particular example of a heat equation, and you start this complicated physical system in some very disordered state. So this is sort of white noise, whatever this is. So there is a paper by Dembo and Mukherjee who make this precise. So this has been around in the physics literature, but there's also this mathematics paper that makes this precise. And then you have a sort of this solution of this physical system started in the disordered state, and you watch this system return to equilibrium. And in this case, you can sort of write down a solution of this and maybe study more things, but in more complicated physical systems, you cannot. But often what you can do is to look at one specific point of the solution, one spatial point of the solution, and observe this and study there, how long does it take to move from its initial state to some sort of one space unit or one unit of u away from where it started. And this is the persistence probability. Yeah? The probability that it takes a long time to get away from to not pass a certain boundary for a long time. So this system also has a persistence exponent which depends on the dimension in this particular case, and this system was studied in the physics literature, and this lambda of d, the persistence exponent, is taken to be a measure for the time it takes to return to equilibrium. Now, there are various other physical systems. I mentioned here only two examples, which are of a similar flavor. So here you have this Burgers equation, which is a sort of deterministic PDE also, and you start this with random initial condition, and you see what are the properties of the solution. Okay, so that's somehow where this question comes from, except of course being sort of also a classical question in probability. Okay, so that was my introduction. What are persistence probabilities? I'd like to talk now about persistence probabilities for Markov chains and its relation to eigenvalues of certain operators. So let us start with a finite state space. So finite state space, discrete time Markov chain. So here I try to sketch such a Markov chain with the state space of a Markov chain. Now what you do is you sort of split the state space into two pieces, and you cut off the connection between the two pieces, and you have one part which is called S, and you are now only supposed to remain in S. So you start somewhere in S, and you are now only moving with your Markov chain in S. Yeah? So you restrict the Markov chain to S. And the question is, what is the probability of remaining in S for a long time? So what is the probability that your Markov chain, that you start in S, so if X naught is in S, you start this Markov chain in S, and you ask, what's the probability that it remains in S until time n, and n, imagine n to be large. Yeah. So if you think of the picture with persistence probabilities, if your original process was a Markov chain, then your set S would be the non-negative numbers. Yeah? And you are supposed to stay in this set of non-negative numbers. I formulated a little bit broader here because I need it in one of the examples. Yeah? Okay, so but that's sort of the question. Okay, so what about this case? So this is somehow classical. What is Pn here, or at least what is the asymptotic order of Pn? And actually, you can also say what happens when you restrict the Markov chain to be in there, or you condition the Markov chain to be in this set. So that's I will formulate in the next theorem, which is a classical theorem that sort of meets only linear algebra, basically. So if P is the transition matrix of the Markov chain, you look at the restricted transition probability. So you consider the transition matrix only on the set S, where you would like to stay with the Markov chain. And if this is irreducible and aperiodic, then you can show that it has well, the largest eigenvalue in absolute value is real and positive. It's called the Perron-Frobenius eigenvalue, and you have eigenvectors to it, left eigenvectors, right eigenvectors, and assume you have a certain normalization. So I made the important thing blue. So the important thing is the eigenvalue equation, of course, but then you sort of normalize the eigenvectors in a specific way. And what you can show then is that the probability that you remain inside the set S until time n, and n tends to infinity, this is asymptotically equivalent to the function h of x. H of x is the eigenvector at point x times lambda to the n, and lambda is the Perron-Frobenius eigenvector, eigenvalue of PS, of the restricted matrix. Okay, so this is the case for finite state space. And the question now comes: what happens if your state space is not finite? What can be done then? And of course, one has to ask for generalizations of the Perron-Frobenius theorem. So there are similar results in the literature for non-discrete state spaces, but they are much more technical and also subtle with respect to assumptions. Yeah? So you have to very much take care what you do there. Yeah? But sort of this is the model for these theorems. Okay, so I would, on the next page, I will not go into the details of the specific assumptions here, because that would be going into the details of our proofs, but I would like to sketch the problems that arise here when you move from finite state space to, in particular, non-discrete state space. So I will try to illustrate on this page the problems that arise when you want to relate when do you want to relate these things. By the way, this is the relation that I was talking about. So you have this probabilistic problem here, and this now is sort of transformed into finding an eigenvalue of a matrix. Yeah. Okay, so what happens in the general state space? Here the setup is as follows. Say E is a metric space, S is a subspace of E, which is the subspace that you want to, or the subset that you want to stay inside with your Markov chain. Xn is a Markov chain on E with a certain transition kernel and with a certain initial distribution. And we are still interested in the probability that this Markov chain remains inside the set S. So I defined PS to be the restricted transition matrix on the last page. So the obvious equivalent would be the restricted transition operator. So, and I use the same notation for this. So PS is now not a matrix, but an operator, and it's sort of, well, it's, let maybe look at this probabilistic interpretation here. So you start at X and you move one step with the Markov chain. If you are in S, then you evaluate your function G, and if not, you get 0. Yeah? So this is the sort of clear equivalent of what is PS in the matrix setting. Okay, and what would be the equivalent of the top eigenvalue? Well, it makes sense to consider the spectral radius of this operator as the equivalent of the top eigenvalue. So the spectral radius of PS is well, is definition, which you know from functional analysis. So that's sort of what you think should be the decay rate of this probability if you only look at the last page. Now, on the last page, P was a matrix, PS was also a matrix. This lambda of PS is the top eigenvalue, and this lambda of PS was the decay rate. However, in the general setting, what you encounter is that this operator PS is often non-compact. Okay, so, and of course, if you want to prove things that you know for matrices, for operators, then it's very good if your operator is compact. So in this case, in the case PS is compact, and you will see that this is not a sort of pathological case. It will happen in very natural examples. So you will see examples on a few pages. So in this case, what may happen is that the spectral radius, for example, is 1, even though the decay rate of this persistence probability here is, well, say lambda tilde to the n, and lambda tilde is strictly less than 1. Yeah, so as you see, it doesn't have anything to do with the spectral radius of PS, as you would expect from the matrix case. And even worse, what may happen is that this lambda tilde depends on the initial distribution. Yeah, so of course that's something that you don't want to have at all. You do want that this probabilistic problem has something to do with the eigenvalue, and if it depends on this initial distribution, then of course it has in principle nothing to do with the eigenvalues. Yeah. So that's certainly what you don't want to have here. So the bottom line of this page is that there are quite a few problems when you pass from this Perron-Frobenius result to general state space. And the idea, and as I said, I don't want to go into the detailed solution. I will just show the sort of resulting probabilistic results. The idea is to apply infinite dimensional versions of the Perron-Frobenius theorem, but not to PS, obviously, because for PS, as you saw on the last page, it will in general not work. One often has to consider a different operator. Sometimes, and that's really the harmless case, the operator PS to some k, to some power works. Yeah, so that's sort of very harmless. Yeah, then except for a few lines of computation, you are in the same nice situation as if you applied it to PS. Sometimes one has to find some other operators. Yeah? And the idea of what I'm going to present in on the next pages is to find a good compact operator such that the persistence probability is really this spectral radius of this compact operator to the end. So the decay rate is the spectral radius of the compact operator. Yeah, you relate this probabilistic problem to finding the spectral radius of an operator, and which is often then also the top eigenvalue of that operator. Yeah, but it's not necessarily this PS operator. So that's sort of the theme of what I'm going to present now. Assume you can relate it, yeah, then this relation between the probabilistic problem on the left and the sort of functional analytic problem of finding eigenvalues or finding the spectral radius can be used to show properties of the persistence exponent. Because sort of if you're on the left, you have not only one Markov chain, but say a family of Markov chains, and you will see this in the examples of autoregressive processes, which are a family of Markov chains. You can show certain properties of these eigenvalues as functions of the Markov kernel. Okay. In some very few examples, you can use this relation to compute the decay rates explicitly, yeah, because you can solve the eigenvalue equation explicitly, and that's sort of the main message of this talk. One can use this relation to compute a series representation of the persistence exponent if your kernel or the operator, and that means the Markov chain, is parameterized by some parameter, say A. Okay, so that's this perturbation idea that appears in the title. Okay, so that was about the relation of persistence probabilities of Markov chains and operators and eigenvalues of operators. I will talk now about what one can deduce from this in the example of autoregressive processes. Okay, so first I will define what is an autoregressive process.
Can I ask one question?
Sure.
If in the previous case, if all the transition kernels are absolutely continuous with respect to a fixed measure, is that a relevant property for these types of questions?
Let's say we don't use that.
Okay, that's not something that comes up anywhere.
Not in our work, no, but I cannot exclude that it's of relevance.
Okay, thank you.
Okay. Okay, so let's start with this example of autoregressive process. Let's define this. So psi I should be an IID sequence with continuous distribution. P be a parameter P, which is the order of the autoregressive process, and boldface A, which means a vector. A is sort of a vector of parameters of this autoregressive process. And then we define an autoregressive process of order P by this formula. So you sort of average the last P values of your process with this vector A, and then you add new noise, a new random variable psi n. Yeah, so this is an autoregressive process of order P. Yeah, and of course we are still interested in the probability of this autoregressive process.
Excuse me.
Yeah.
You said average. Does that mean you're assuming that the sum of the AJs is 1?
No, I'm not. It was just for illustration. You're right. I mean, it's in general not an average. No. So the A's can be negative. They can be. They don't have to sum up to 1. No. So the assumption is really here as it says. So actually, they can all be negative or all be whatever. No. So. Okay. So. What we have to do here, or what we do here, is to distinguish 3 cases. One case is that all the A's are negative. Second case is that all the are non-positive. Second case is that they're all non-negative. And the third case is that the sum of the absolute values of the AI is less than 1, which is sort of the strongly stationary case. So actually, if you have the modulus sign outside, then this is the case where this process is stationary. So this is even a more stronger restriction. Okay. So in these 3 cases, we can say something about the persistence probabilities of for autoregressive processes and the relation in particular to operators. Okay. So I'll talk about these 3 cases now. First case is where all the A's are negative or non-positive. In this case, this is sort of the case. Well, sort of one harmless case. In that case, one can apply infinite dimensional versions of the Perron-Frobenius theorem and show that the persistence probability, which is now a function of the vector A, has decay rate lambda to the lambda of A to the n, and lambda of A is independent of the initial law. And if lambda is positive, then it is the largest eigenvalue actually of the canonical operator that belongs to this process. Note this process is not a Markov chain, but you have to take sort of p values of the process. So xn minus 1 up to xn minus p plus 1 or so. So this is a Markov chain. Yeah? And this has an operator ps that belongs to that, and the lambda that appears here in this decay rate is the largest eigenvalue of that canonical operator that belongs to this Markov chain. Yeah? I don't write down the operator because, as you see, it's already quite a long vector here, and if you write down the operator, it's becomes even longer. But it's sort of kind of a harmless case. Okay. Then there are conditions when this decay rate is positive or less than 1. So, and which is sort of easy probabilistic argument. This has nothing to do with this relation to operators. So if you can stay positive, sort of then if you have a chance to stay positive, which means your noise is allows to be positive, then the decay is not super exponential. Yeah? And if you're not necessarily positive, which means your noise allows to be negative, then the decay rate is truly exponential. That's what is said. So that's sort of very natural in this context. And what we can show is that the map that maps your parameter vector A to the decay rate is continuous, on the range that we are looking at. Yeah. That's certainly something that is at least I think impossible to show on a probabilistic level. So if you can show this probability, even if you can show this here in a probabilistic way, I don't see any way of verifying that the resulting decay rate is continuous in A. Yeah. That's something that we show with the help of the relation to eigenvalues of operators. Okay, second case is the case where all the A's are non-negative. Okay, and in this case the whole relation breaks down. So that's sort of the case opposite to the last page. On the last page everything was fine, and there was this relation to eigenvalues. Here there's no relation to eigenvalues. Okay, so the theorem says as follows: if all the A's are non-negative, then the probability that your autoregressive process remains non-negative while it's also decaying exponentially, but this decay rate in general does depend on the initial distribution. So mu is sort of p, x, say x naught up to x p minus 1 or so. Yeah, so the initial distribution of your Markov chain, of your autoregressive process. If your autoregressive process is of order p, you have to put p of the values as sort of initial values to start the process, and in general, in this case, the decay rate does depend on the initial distribution. Okay, so in general, there's no connection to eigenvalues. Actually, I could cross out here the in general, because this just says there's no connection actually in all cases except for trivial ones. So the fact that still there's a decay exponent, that there's still exponential decay and this still exists, is due to a probabilistic argument due to non-negative correlations. So in this case, if all the A's are non-negative, the process is positively correlated, and you can do some argument with non-negative correlations. Yeah. So the example that shows that that things do depend on the initial distribution is as follows. So take an autoregressive process of order 1. This is this process here. Yeah, so this is p equal to 1. Should put an A1 here, but okay, for simplicity, let's write A. So this is your process, your autoregressive process of order 1, and let's say the xi I are plus minus 1s with whatever probabilities. Yeah, so it can take them just fair coins. And now you start at some value x naught, and you are sort of multiplying the current value always with some number a, and then you add a fair coin, say. Yeah. Of course, if a is greater than 1, your process will certainly move towards infinity, because you say you multiply by 2 your current value, you multiply by 2, and then you add a plus or minus 1. That will sort of make you escape to plus infinity. Yeah, so that's not a very interesting case. But say if a is less than 1, then your process has, of course, a tendency to go to 0. However, if your initial distribution is sort of sufficiently heavy-tailed, yeah, so if you start well enough positive, yeah, then even though your a, say a is 1/2, will bring you to 0, yeah, it will take a while, and by making this x naught sufficiently positive, you can make this process survive until time n. Yeah. So if you are allowed to choose this x naught sufficiently heavy-tailed, then the process will, whatever the coins give you, the process will survive until time n. Yeah? So actually, the probability that this process x1 and so on until xn greater or equal 0, this is something like the probability that that x naught is sufficiently large, yeah, which now depends on n. So I don't want to write down the exact formulas, but somehow you can reformulate this in terms of the initial condition. Yeah? And if your initial condition is sufficiently heavy-tailed, then this rate here depends on how heavy-tailed this initial condition is, and you can vary the decay rate, and you can in particular make it dependent on the initial condition. Yeah? So this is not a very unnatural example, and which shows that in this case there's no relation at all to eigenvalues of the transition operator. Okay. Okay, so now let's look at the third case, which is again a good case, not so harmless as the first case, but a good case. So here you can allow AIs to be positive, but the sum of the AIs, modulus of the AI, has to be less than 1. So in this case, we are back to the situation where everything is good in some sense. So here again, the persistence probability has a decay rate that does not depend on the initial condition. So I do put more assumptions on the initial condition. They are supposed to have finite exponential moments here. Yeah, and then we can show that this decay rate does not depend on the initial condition. And if it's positive, so that means if the decay is not super exponential, which is sort of the natural case, then it's again the largest eigenvalue of the canonical operator. Yeah, so that's again a good case. Yeah. And we have this relation again between when is lambda positive, which is the natural relation that I showed you already 2 pages ago. And again, we can show that this map is continuous. Yeah, that was something I showed also in the case where all the A's are non-positive. Yeah, the map that maps the parameter vector of the autoregressive process to the decay rate of the persistence probability is continuous. Okay, a quick digression from this to monotonicity of the exponent, which is also something we can show with the help of the relation to eigenvalues. So here I only repeated the definition of the autoregressive process. And if it exists, then the probability that this autoregressive process is non-negative until time n has a decay rate lambda of A. And we address the question, is this decay rate, is this monotone in A? Yeah, and the theorem here is as follows. Under certain assumptions, I don't want to mention all the sort of reasons for these assumptions. So the psi I have to have a strictly positive log concave density. Think of something like a Gaussian. The A's are non-negative. I will comment on this after the theorem. And we are in this third situation where there is a relation between eigenvalues and decay rate. Then, first of all, if the A's, all the A's are less or equal the B's, yeah, a certain vector B, then the decay rates are ordered. This
is just checking, you're comparing entry by entry, right? A is less than B, and bold means?
Yes, yes.
Okay.
So bold A less or equal B, bold B means all the A's are less than all the corresponding B's. Yeah, so. Yeah.
Yeah.
Component-wise. Okay, so the first statement here is non-surprising somehow, and it's a simple coupling argument. Imagine the x or the x values are already non-negative, and the A's are less or equal than the corresponding B's. Then, of course, you can replace the A's by the B's, and the sort of the process that is given by the B is always above the process that is given by the A's. Yeah, so x sort of the process that you get from the A's, from the A vector, which is this thing here, this process is always below the process with the B's. Yeah, you can couple them, and if you use the same Xi variables, you can show that this is true. So that easily gives you this this conclusion here. What is non-trivial and where we do use the connection to operators is the second statement. So if the bold A is less or equal to bold B, and they're not equal, that means one component in one component the B is really strictly greater than the corresponding A. Then the exponential decay rates are different. So you gain an exponential factor if you if A is not equal to B. Yeah. So that's a deeper result and non-trivial, and that really exploits the connection to operators. Okay. Okay. So as I said, I wanted to. Yes.
Why is the condition about sum of AI important?
Well, it's important because in the case that the A's are non-negative, in general, this lambda of A would depend on the initial distribution. Yeah. So if I only impose this condition here, then this could depend on the initial distribution. And then I start. I mean, of course, this thing is still true.
Okay, I see.
This is still true. The coupling argument is still true. Independent. I mean, this if you take the same initial distribution, this thing is still true. Yeah. But I think this I'm not exactly sure, but I think this second statement is not true in general. If you just if you only put the A's to be non-negative. Yeah. So this condition ensures that the decay rate does not depend on the initial condition.
I mean, you could have claimed the second bullet for certain initial conditions, like to couple them as well, perhaps. But yeah, my question was, what is like this condition of some AI? Yeah, does it give you perhaps some extra property that you're using? But
I'm not sure actually at this moment.
Okay. Mm-hmm.
Yeah, it's a valid question. I don't know.
Okay, good.
Yeah.
Thanks.
Okay, what I do have to assume is this condition, because one can show that outside this, the A's are when the A's are non-negative, there's no monotonicity in this sense. Yeah, that's not difficult to see.
Thank you. Yes, I believe that. Yes.
Okay.
Thanks.
Okay, so that was for for the results about monotonicity. I would like to quickly mention two other papers. One is which deal with the same type of questions. One is by Hinrichs, Kolb, and Wachtel. They consider one-dimensional autoregressive processes and make further assumptions on the innovations, something like bounded innovations and so on. And they can show more precise results. So what I was interested in is the exponential decay rate. They can show things like this, that the exact asymptotics is some function v that depends on the starting point, while as I said, I can only say something about the lambda here, and I can relate lambda to eigenvalues, but I cannot show this type of precise behavior. Okay, so they have a completely different approach to this sort of more using quasi-compactness things, and they develop a renewal type equation for this type of problems. So that's completely different. And then there's another paper by Dembo, Ding, and Yan. They consider the Gaussian case, so they consider d-dimensional or sort of p-dimensional autoregressive processes with Gaussian innovations. And they are interested in showing when the persistence probability actually has exponential decay, which is always implied in our case. So our assumption always implies, if they hold, then they apply exponential decay. But you can imagine autoregressive processes where the persistence probability tends to a constant, or has stretched exponential decay, or has polynomial decay. Yeah, so these things are possible, and they in their paper they characterize when is either of these behavior is true. Yeah, and what they use is the roots of the characteristic polynomial. Okay, so much for related work and for sort of results for autoregressive processes. I would like to introduce now this idea of perturbation theory for the case of autoregressive processes of order 1. Okay, so here I repeat the definition of an autoregressive process of order 1. So xi I is an IID sequence with a certain density. A is some parameter that from the start I restrict to the interval from -1 to 1. And then we have this autoregressive process. And we are interested in, and I should say that that the initial condition is also Gaussian. So, that's important here. Because as we saw, things do depend on the initial condition. Yeah, so the initial condition is Gaussian here also. And then the probability that this autoregressive process of order 1 remains non-negative is lambda to the n with some lambda. And lambda is the eigenvalue or top eigenvalue of this very concrete eigenvalue equation. So as you see, it's a very concrete equation. Yeah, phi is the density of your innovations, g is the eigenfunction, and lambda is the eigenvalue. Yeah, so if you can solve this, well, solve or sort of find the top eigenvalue of this very concrete eigenvalue equation, one has the decay rate of this persistence probability. Yeah. Okay, so we are interested in the top eigenvalue, which is of course a function of A. Yeah, A is the parameter of this autoregressive process. So the eigenvalue, in particular top eigenvalue, depends on A, yeah, on the parameter of the autoregressive process. And of course also the eigenfunction depends on the parameter A. Yeah? And now we are only going to look at this eigenvalue equation. Yeah? And we're going to see how this can be sort of expanded in the parameter A and how this can be used to find at least a series representation for lambda. Okay. So let's look at only this this innocent looking eigenvalue equation, yeah, which is the eigenvalue equation related to autoregressive processes of order 1 with Gaussian innovations. So this, as I said, lambda is a function of A, G is also a function of A, yeah, of the parameter of the autoregressive process. And assume you can expand this, so you can write down a series for lambda in terms of A at A equal to 0. Yeah? And assume you can do the same for G. So then you get this stuff here. So of course, it's not important to look at the details. The important thing is to see that lambda has some series representation, and G also has some series representation, which is now, yeah, say a function or a series in A and X. Yeah? Assume one can do that. Yeah. Then you have this terribly looking equation. You can exchange sums and integrals. Assume you can justify all this stuff. Yeah. Then what it turns out that you can find an iterative formula for the Ki. So Ki are the coefficients in the series representation for lambda. Yeah. Recall we want to compute lambda. Yeah. We're given phi, the density of the innovations, and we want to find the top eigenvalue of this equation. So we want to compute sort of the largest lambda for which this is true. And if we can compute the Ki, yeah, for this top eigenvalue, then, well, what we have at least is a series representation for lambda. Yeah, we don't have an explicit formula maybe, but we have a series representation. Yeah? So we can write down lambda as a series, and if we know the Ki, well, we think that we know lambda, right? And what we can show is that at least for Gaussian innovations, for Gaussian phi, this procedure can be justified. Yeah, so there are some things to be justified. The most important thing is that lambda and G can be expanded in A. Yeah, and I will sketch in not on the next page, but after that how this, or an idea how this can be proved. Yeah, but that's sort of the main thing to show, that one can expand these things in A. And then, of course, it's interesting, what is the radius of convergence of this series here? And here we can show that this radius of convergence is at least 1/3. Yeah, I believe it to be 1, but which would be the sort of the natural radius here, but we can show that it's at least 1/3. And as I said, the Ki can be computed explicitly. And you will see on the next page what explicitly means. So they are explicit, and actually they're too explicit to guess a formula. Of course, if you have an idea what would be a closed form formula for the coefficients on the next page, I would be very interested. So I did compute for quite a while, and so did my co-author. But yeah, so the coefficients, as I said, can be computed very explicitly, and here are the coefficients. Yeah. So this is, yeah, it's very explicit, which is nice, and of course I can compute K8, K9, and so on. But
you've checked the encyclopedia of integer sequences, I assume.
Yes,
okay.
Yes, very often, yes. Yes. So actually, we do have a formula for these last things, yeah, and I think also for these. Yeah, but even though having these two formulas, we don't know what is sort of the next term here. Yeah, I mean, of course we can compute it each time, but I don't have a closed form formula for this. Yeah, it actually would be quite, I mean, because I've spent a lot of time on it, I would be very interested in finding a closed form formula, obviously. But yeah, that's somehow where we are. Okay. Okay, so let me get back, or let me show you an idea of the proof of this perturbation result. So recall that the persistence probability is PS to the n. PS is a restricted operator applied to the constant 1 function.
Excuse me, one moment. These numbers, they're in your papers. I mean, I can find them.
Yes, you can find them. So this is the paper with Marvin Kittner.
Thank you.
I mentioned it on the last page. Yes, and actually there are more coefficients for the moving average case, which I haven't talked so far. And if I look at my stopwatch, and I think I will not talk about this, but there are similar coefficients, which I also don't know what is the closed form formula for this. Okay. Okay, so yeah, quick idea of the proof. We are interested in this persistence probability. We can express it with the help of this restricted operator PS. So this is the canonical operator in this case. Yeah, very explicit. And the trick now is to move to a different space. So the canonical operator works on, say, bounded functions. And the trick is to rewrite this operator and have it map on a different space. So the only thing we are doing somehow is to replace this blue stuff here by integration with respect to standard normal distribution, like with the Gaussian standard Gaussian measure. So the two blue things are sort of inequality. Yeah. So I'm choosing MA. Of course, this whole thing depends on A and X and Y in such a way that the integration is now with respect to the standard Gaussian measure. Yeah. So this is I'm equating these two things. So this is sort of the definition of MA of X and Y. And I'm not looking at bounded functions, but I'm looking at functions in L2 of gamma. So things that are integral or square integral with respect to the Gaussian measure. Okay. And suddenly this thing becomes much nicer. I mean, only looking at different space and rewriting this, it becomes much nicer. So the first thing, of course, is that L2 is a Hilbert space, which is very nice if you want to do this perturbation theory. And the second thing is that this MA here splits off into a series in A, yeah, and to an explicit series in A. And this allows to write this operator MA, which is now between Hilbert spaces, as a series of in A, yeah, with operators m to the n, which are independent of A now. Yeah? And the idea now is to use sort of perturbation theory for linear operators. There's this book of Kato, and there you can look up some things. We actually reproved most of the things because the things that we found in Kato's book were not exactly to the point that we wanted to use. But the idea is to see that if your operator can be written in such a way and you can control the operator norms of the MN, then you can show that this is a holomorphic operator. Holomorphic here means that, well, it's a series on a non-trivial disk around zero. Yeah. And then what comes then are things that are motivated by these functional analytic tools from this book by Kato. Yeah. I don't want to go into the details here. We've basically reproved these things in the paper because, as I said, we could not use exactly the theorems from Kato. Okay, so that's the whole idea of this perturbation theory. So I have a fifth part now, which I will sort of go over very quickly in the interest of time. The results are sort of very similar or parallel to the autoregressive case. So a moving average process is well, you take noise, you take psi I, so IID, an IID sequence, and you average this. Average again, not in the sense that the A's have to sum up to 1, but sort of you have a filter basically. Yeah, you take this noise and you move it over this filter. Then the first thing to ask for is the relation between the persistence probabilities of this process. Again, this depends on the vector A to eigenvalues of certain operators. And here, in all the cases, so for any A, yeah, we don't have to distinguish cases. There is a relation to the to eigenvalues. So this decay rate is a function of A. And this, if lambda is positive, it's the largest eigenvalue of a concrete operator. Yeah? And this eigenvalue is positive if and only if the sum of the AI is not equal to 0. Yeah, so that's a nice condition that ensures that there is this relation between decay rate and eigenvalue of an operator. And this map again is continuous. So the map that maps A to the decay exponent is continuous. Yeah. Comments. First, there's no monotonicity here, which is a natural thing. One can show that this function is simply not monotone because there are non-trivial relations of this thing. And second thing, this third thing was proved by Ohad, who invited me, but who has teaching now. So yeah, thanks to Ohad for giving a nice proof for this. Okay, so this was the existence and properties slide for moving average processes. There's also a perturbation slide. So here again, I rewrote the definition of a moving average process of order 1. And I again take Gaussian innovations here. And I'll have A between -1 and 1. There is this relation to eigenvalues. And again, we can use the perturbation approach to show that this lambda of A has a series representation in A. And we can compute these Kn prime explicitly, so the coefficients of the series representation of the thing that we're interested in. And on the next page, you will see again these explicit numbers. Yeah. So these are the explicit numbers here. Again, I can compute more of these numbers, but I don't have a closed form formula for this. So these things are not yet well, not yet available on arXiv or so. But if you're interested in these numbers and trying to solve this for a closed form formula, I can of course send you the draft that we have already. Okay. Yeah. So also here, the proof idea is to rewrite things in such a way that the operator that appears at the end is a holomorphic operator, and you can apply this perturbation theory for linear operators, or the techniques from Kato's book somehow. So here, after a few trivial transformations, you can relate it to this specific, the problem to this specific operator here, which looks very similar actually to the operator in the autoregressive case. And again, the trick is to ask what space do you have to make this operator work on? Yeah, and in this case, there is a certain Hilbert space that we look at, Hilbert space that is spanned by Hermite polynomials, and on this space with a certain scalar product. I think the details are not that important, but the major thing is that this operator on this space can be written in such a format, so as a series of operators, Tn, and we can control the operator norms of these Tn's, and all this makes the perturbation theory from functional analysis work. So that's sort of the idea here. Okay, so let me come to a summary. We've seen persistence probabilities for Markov chains. So for Markov chains, the rate of non-exiting a set S, or remaining sort of in the non-negative half-axis, is typically exponentially decaying with a certain lambda, which is the spectral radius or top eigenvalue of an appropriate operator, at least if things work. It's not necessarily the canonical operator. Yeah? Usually it's hard to compute lambda. I mean, of course, it's hard to compute lambda explicitly. It's already hard to compute eigenvalues of large matrices. So yeah, it's obviously also hard to compute eigenvalues of certain operators explicitly, but this eigenvalue representation can be used to verify properties of this decay rate here. Yeah, so things that cannot be done probabilistically. And by properties, I mean something like monotonicity, strict monotonicity, or continuity if you have a family of Markov chains. Yeah. So we saw this in the case of autoregressive processes and moving average processes. And one can use this to make a perturbation argument to find a series representation of the top eigenvalue in terms of the parameter of the Markov chain. Yeah, so the crucial point here is to write the eigenvalue equation that is related to this probabilistic problem, sort of as a function of a of the parameter of the Markov chain, and the operator that is relevant here. If you can write this as a series and show properties of the series, in particular, control the operator norms of the operators involved here. And if you can choose an appropriate space where all this works, then one can apply results from functional analysis to show that also lambda, the eigenvalue, and g, the eigenfunction, can be written down as a series. Yeah? And then in some cases we computed the coefficients of the series expansion. Okay, so that's the end of my talk. Thanks a lot for your attention.
Thank you very much, Frank, for a very nice talk. Any comments or questions?
I'd like to ask one question. Way at the beginning, in the general context of a stationary process, you mentioned, you could try to get the lambda corresponding to it for the decay rate, and then you analyze in a lot of ones where you could compute the lambda. Have you thought, my guess would be in the general context of a stationary process, that you probably could get it so that at certain ends it decays like with a large lambda, and for other large values of n, it can decay for a small lambda. In other words, it's not a well-defined exponential decay rate. Have you looked at that at all?
Not sure I understood your question correctly. So what you say is that it may happen that that there is no decay rate?
In the complete general context of a...
Absolutely. I mean, absolutely, there are examples where there's no, I mean, this thing that I mentioned at the beginning, it may happen that there's no decay rate. Yes, absolutely. So maybe,
when you say no decay rate, Are you referring to decay rate 1, or I'm referring to a fluctuating decay rate?
Yes. This
Okay.
may happen as well. Yes.
You have that.
Yes.
Okay.
Yes.
I didn't hear that.
Yes. Sorry. I mean, the introduction
I missed it.
maybe a bit too well, optimistic, or so I guess. I guess you're referring to this page, right?
Yeah, exactly.
Yes. So it's not true that for general stationary processes, there's always a decay rate. No, not at all. Even in the examples that we considered, you can cook up examples where there's what you call fluctuating decay rate, or even worse things. So certainly this is not. It's just that's why I wrote we expect, or we would wish to have, or something. But certainly there are pathological or not so pathological examples where this does not for sure.
Okay, thank you.
So Frank, you mean examples within AR and MA processes?
Within AR, yes.
Within AR, yes.
Yeah. Yes, they're actually in our paper. So yes, this it exists. So that's clear. Yes, I mean I try to stress in the results, where the positive results, where there is a decay rate and properties of the decay rate and the relation to eigenvalues. But certainly there are cases where there's no decay rate in this sense. Yes, you are right.
Yes. Any other comments, questions?
You found a situation in which the exponent is continuous in terms of the A's, but in this case, is it actually analytic, at least near the origin?
In general, we cannot show this. If you ask for all the AR cases, in general, we cannot show this. In the case of autoregressive 1 with Gaussian innovations, yes, it is analytic at 0. Yes, but in general,
but for larger AR, it's not shown.
It's not shown. No, I think one can use this perturbation technique to show it, but it's not shown. No, for sure. And also for other innovations. I mean, we showed it for Gaussian innovations. I believe that this is true in much more generality, but as you maybe saw in the ideas of the proofs, we use an explicit transformation for the Gaussian measure, and then we have space with the Gaussian measure and so on. So this does depend on, at least our proofs at the moment depend on the assumption of Gaussian innovations. I do believe that this is true much larger, but in a much larger class. But that's what we can show: AR1 plus Gaussians.
Okay.
But I believe that.
And is there any meaning for if you have a singularity, like any probabilistic meaning, or is this not clear?
That's a good question. What I think, even though also I have not shown this, is in the moving average case at 1, I think there should be some sort of singularity, because there you have a super exponential decay at -1 rather. So the result shown by Ohad, and I think there should not be analytic. But in this particular example, I can give a probabilistic sort of explanation for it, even though I have not shown that it's not analytic there. But in general, whether analyticity has any probabilistic meaning, I don't know. And even I mentioned that we proved certain radius of convergence of this series that is larger than 1/3 and these things. So it may happen that in the functional analytic setup you have some eigenvalues in the complex eigenvalues that sort of make the radius of convergence sort of artificially smaller than what you would expect from the probabilistic problem. So maybe there's some I don't know, some artifacts that you don't see in the probabilistic problem. So that, if that's an answer to your question, I don't know.
Thanks.
Any other questions? Okay, so let's thank Frank again. Thank you very much for coming to JIPS for the very nice talk. So we meet next week. Stay tuned. So Frank, yeah, I'd be happy to ask some more questions, but
Sure.
let's give the chance if someone else wants to stay to discuss.